Welcome to the 12th chapter on ghosts and differential ghosts in the Logical Foundations of Cyber-Physical Systems textbook, where we will see yet another fundamental reasoning technique for differential equations, this time using the admittedly somewhat surprising use of additional auxiliary variables that are called ghosts. A discrete ghost, well, that's an extra variable that's introduced into a proof or a model with an assignment for the sake of analyzing that model. A differential ghost, that's an extra variable that's added into the dynamics of a system with a very arbitrarily made-up differential equation merely for the sake of analyzing the system. Both of those sound pretty counterproductive because they increase the dimension of the system, but when we look closer, we'll find that differential ghost variables provide additional quantities relative to whose quite arbitrarily chosen continuous evolution of the behavior of the system can be much better understood. If we find a clever choice of the new differential equations for the differential ghosts that we merely made up for the sake of analysis, then it becomes much easier to understand the evolution of the original variables. What have we seen? We've seen differential invariants as an induction-based proof rule for differential equations merely based on their right-hand side instead of the much more complicated global solution. We've seen differential cuts that first prove another property and then change the dynamics of the system by adding the property that was just established to always hold after the ODE into its evolution domain constraint. Differential cuts are a fundamental proof principle because there are properties that are only inductive thanks to the use of differential cuts. They change the evolution domain constraint, but soundly so after we've done a suitable proof of invariance. Differential ghosts soundly change the differential equations themselves, and that, of course, should make us even more nervous about soundness. Why on earth is it okay to edit the differential equations? We'll see how that can work. Differential ghosts add an extra variable that is introduced into the differential equation system solely for the purpose of the proof. And this existence for analytic purposes is where this admittedly rather spooky name ghost comes from. Ghosts, or auxiliary variables, they don't really exist in reality. Ghosts are not really present in the actual system, but just invented to make the story more interesting, or rather to make the proof more conclusive. We'll also see discrete ghosts that remember an intermediate state during the execution. Why would that be helpful? Well, because we can remember in a new variable the value of an old state from a little while ago, and that can sometimes make it easier to analyze the change of an expression compared to what its value used to be way back when, compared to analyzing the expression itself. Discrete ghosts merely restore with discrete time updates old state, but differential ghosts also evolve themselves continuously over time along a differential equation. Both of them give the proof a way of referring to a state that isn't the actual true state of the system at the moment. So what we're going to see is, from a modeling and controls perspective, in this chapter we'll learn nothing at all. Why? Well, the whole point of the ghost variables is that they're merely there for the sake of the proof and not for the real system. They're made up for the analysis purposes. Okay, admittedly, we'll learn a little bit in terms of modeling and control still, because sometimes it is useful to write down the ghosts in the model regardless, but then you should really be marking them as ghosts and to make sure that you're not surprised when you don't find them in the execution of the system at the end. And we'll also enable us to get a better understanding of how to work with solutions of differential equations without actually working with solution axioms for differential equations. A lot of what we focus on in today's chapter, however, is on the computational thinking side, even more advanced rigorous reasoning for even more complicated differential equations using extra dimensions for extra invariants, which sounds like, from a state space perspective, the most horrible idea ever invented because, well, just when you even think about the number of points that you get when gridding the state space, that grows exponentially in the number of variables by the curse of dimensionality. So don't ever make the state space bigger. It doesn't help intuitively to reduce, quote unquote, the analysis of a 10-dimensional differential equation to an 11-dimensional differential equation. But it turns out, from a reasoning perspective, this extra ghost state variable can sometimes help and make reasoning possible that wasn't otherwise possible. Another way of understanding that is essentially a proof counterpart of what it took to invent dark energy. We're observing that things don't quite balance out and hypothetically make them appear for the sake of our analysis. We'll see that in more detail later on. What we see today is not important for all advanced cyber-physical systems models, but it is certainly quite important for the most difficult and fundamentally tricky one. From a CPS skill side, we look at a better intuition for operational effects of CPSs in terms of how we can relate state as opposed to just worry about the present state, by using extra ghost state variables that merely remember things or remember other quantities relative to which we want to understand the evolution of our own system. So let's get going. What we have seen are the differential weakening proof rule. That is a very simple one that proves a post-condition of a differential equation system limited to an evolution domain constraint Q in case we can establish the post-condition F just from using simply the evolution domain constraint. Sure, by differential weakening, if a property is true everywhere where the system is allowed to evolve to, then, well, it is true always after we follow the differential equation, no matter what differential equation it actually was. That simultaneously tells you how often differential weakening should be useful. It really only should be useful for systems with very informative evolution domain constraints, which, remember, however, are essentially assumptions on the behavior of the system. But differential weakening can also be useful after we have successfully enriched and augmented our evolution domain constraint beyond what it was initially, using the differential cut principle. But we're getting ahead of ourselves. The differential invariant proof rule proves, as the name suggests, an invariant f of a differential equation system whenever its differential, so the logical formula f prime, can be proved to hold within the evolution domain constraint after assigning the right-hand side of a differential equation to the left-hand side of a differential equation in just a discrete assignment compared to a differential equation that has a continuous dynamical systems effect. So this basically works about how truth values change locally, which is where the differentials and the differential formula come from. And the differential cut proof rule proves a property of a differential equation by first proving something else, a property C, proving that we can't leave C when following the differential equation, and then editing the differential equation's evolution domain constraint by adding in the conjunction that instead of just not leaving Q, now we're not allowed to leave the conjunction where Q and C is true. But that, even if it should make us nervous, was actually okay because we previously established in the left premise that we can't leave C anyhow. Also remember the differential weakening, differential invariant, and differential cut proof rules really derive in a very simple, straightforward way from the differential weakening, differential invariant, and differential cut axiom, which are the more fundamental principles. But these are already packaged up properly for use. Also remember, there was a differential effect axiom that we used to tease out in an assignment the effect that a differential equation has on its primed symbols. After this review, let's spend some time to gradually motivate and introduce ghost variables. Well, of course, ghost variables are meant to be introduced in any case into the proof, but the point is we will one step at a time understand what we could possibly be using them for before we get to the actual differential ghosts topics. First, the discrete ghost proof rule. A discrete ghost is just, a new variable y that we can dream up arbitrarily that remembers the value of a term e that is very dear to our hearts. We just want to remember what is the value of e at the moment before we make progress, and then store that in the value of the variable y, which we dreamed up fresh. Otherwise, we wouldn't be remembering anything new, right? We would be changing the dynamics of the system if y would already appear in p. That would be very dangerous. What could we use that for? Well, here's one example. It is a very simple one, but it'll suffice for us. If you would like to prove that whenever xy minus 1 is 0, then after following x prime equals x and y prime equals minus y, so rotational dynamics, does xy remain 1? Could be worrying about this directly, and in fact it'll succeed, but then I wouldn't be showing you the role of the discrete ghost proof rule. So instead, let me use the implies right proof rule to push the assumption on the stack, and then introduce a ghost. The quantity that I'm excited about is the product x times y. So how about we do this proof not by worrying about whether xy equals 1 all the time directly, but instead by relating how the value of xy changes over time. For that, of course, back here, we can't talk about xy from the initial state because both x and y have already changed their value while we're at the post condition. That's after the ODE, remember? So instead, we'll introduce a discrete ghost to remember what the value of x times y used to be before the ODE. So let's introduce a new discrete ghost that remembers the function of an old state. It will remember what x times y used to be back here before the ODE started. And then the idea is, since c is new, if we ever refer to c in the rest of the formula, we will actually be referring to the value that the product x times y used to have before the ODE ran. And then the idea is, if we relate how c changes to how xy changes, well, c doesn't change, then we also establish this indirectly. That's now the next proof rule to use. Well, we've got an assignment to worry about, right? So I guess we're using the assignment axiom. What will that do? It will plug in the value of c everywhere. Actually, that doesn't appear. So if we were to do that, this thing would go away, and we would be left with the question we had a moment ago. That's brilliant. We could then introduce yet another discrete ghost, and then make it go away again, and another discrete ghost, and make it away again. But, of course, you get the point. It's not like, even though we would be using a lot of proof rules all day long, we wouldn't have exactly made a whole lot of progress in our understanding of the question. So how about we don't do that? Well, what else could we possibly do with an assignment? Indeed, we could remember the effect of an assignment by an equation. So we could say whenever we have an assignment, that we remember the assignment as an equation and then continue proving P. Well, that actually wouldn't be a very good proof rule to adopt. So we can remember the effect that an assignment had in an equation c equals x times y, so that it doesn't go away. Well, let's understand the proof rule that we're using for the job. So in order to prove that after assigning e to x, p is true of x, we can just remember the value that x has in an equation y equals e, and then prove p of y instead. Well, actually, we probably could have just used x here. But the point is we can't. And it's important to understand why. Well, suppose e would include the variable y. For example, e would be y plus 1. Then here, for assigning x plus 1 to x, we would here remember the equation y equals y plus 1. And it's very easy to prove all kinds of things from the assumption that y is its own successor, which it really never is. So it's important that the variable is a new variable that we're doing here, to make sure that the variable we remember it in isn't the one we had. And now we can make progress by monotonicity principle to prove, instead of proving that xy equals 1, we prove that xy doesn't change its value, so xy is equal to the value c that it used to have from way back when. The product it used to have in the beginning is still the same value, and indirectly that of course means we have proof that it's always 1. The monotonicity proof requires us to prove that if c is equal to xy, it also is equal to the value 1, and that will work with a little bit of extra effort in monotonicity because c is a constant, so it doesn't change here. So from these two you can conclude that c actually has the value 1, and so the proof over here will succeed by a generalized version of monotonicity as well. The point is, now here we're left with a question about how the value of xy changes, never mind what it used to be, and then we can use straight out differential invariance for the job by putting the prime over the post condition, which will give us the differential of the discrete ghost c is of course 0 because it doesn't change in the differential equation. Could plug in c prime equals 0 basically. And then we plug in x prime's new value here and y prime's new value here, which will give us this, that 0 is x times y plus x times minus y. And of course, xy plus x minus y just cancels out, so this proof is now trivial. The point is not that this is a better way of proving this particular property. The point is merely to illustrate how can you remember old state with a discrete ghost and prove in relationship to that. We can now use this technology to do a proof of quantum the bouncing ball using no solution axioms. Remember, in chapter 7, we were very proud of ourselves to have the first proof of a bouncing ball repetition loop, but we used the axiom to replace differential equations by their solutions and the quantifier over time. That was fine, but suppose we don't want to do that. Why? Well, because solutions axiom, oh my, is that a complicated axiom to be using. Besides, we got in trouble sometimes with writing down solutions that turned out not to be the right solutions, and then the proof was awkward. How can we once and for all do proofs of bouncing balls without the solution axiom? Well, we had such a proof already in the previous chapter, where we proved this property is the core argument behind the bouncing ball's correctness using differential invariance. So what we remember, we split the proof by a box and distribution, and then we did a differential weakening argument on the right and a differential invariance argument on the left, and then all worked beautifully. But the point is that we needed to have just exactly the right invariant for this proof to work, even if it didn't use the solution axiom. So instead, let's understand how can we directly mimic the effect of the solution axiom without actually using the solution axiom. So let's just remember, for example, one of the questions we had is that if we start in an initial state that looks like that, does a final post condition maybe like that work out for the differential equation dynamics of the bouncing ball? And let's never mind about these two. Let's just forget that and worry about A formula A that fortunately we forgot, and a formula B that fortunately we forgot. How can we prove this property of all behaviors along a bouncing ball dynamics to remain within, well, some formula B of x v with solutions? But of course, with solutions, but not using the solutions axiom. So one step at a time. What is the solution of these differential equations? Well, it's going to be a new value for x and a new value for v. As a function of time. So for velocity, it's going to be the value of the velocity minus gravity times time. Wait, that can't be right. I forgot the dependence on time. And for position, it's going to be plus velocity times time minus half gravity times time square. Oh, wait, I forgot the dependency on time. So here we go. Okay, so how can we prove this solution and make use of it somehow, but not using the solution axiom again? Well, the point is, I guess, if these are the solutions of the differential equation, they should be invariant along the differential equation, right? Because a differential equation has the same solution at every point, otherwise it wouldn't exactly be called a solution. So we should be using a differential invariant argument for that. But of course we can't, because even if the solution is invariant along a differential equation, we can't just talk about x of t, because, well, x of t isn't even in the syntax of what we've seen so far. Well, so what is the value of x at time t? Well, that's of course just x, right? Hold on a second, that can't be right, because now we have an equation that v equals v minus g times t, which is rarely the case, unless either g or t are 0. And of course on this side we don't actually mean the current velocity. Here we do mean the current velocity, but here we do mean the initial velocity. How can we call that? Well, we can call the initial velocity v naught. Why not? And likewise up there, we can call the initial position x naught. Here you make reference to the initial velocity v naught. Great. So now we have a beautiful equation that we can prove to be a differential invariant. How? Well, for one thing, if we want to prove this to be a differential invariant, we had better make sure that x naught and v naught actually are the initial values of the position x and velocity v. How could we do that in a proof? Well, we could edit the model and make it so, but then we would be introducing state into the model merely for the sake of our analysis, and that is exactly what makes these things ghosts. So, for ghosts, we also do have proof rules. We could introduce variable x naught and variable v naught that remember the initial value of x and v by a discrete ghost. Also, how do we then prove this to be an invariant? Well, we do a differential cut with this equation and then use a differential invariant argument to prove it. Will that work? No, it won't, because this is only the solution of this differential equation x prime equals v and v prime equals minus g if we already know the behavior of the velocity v, which we don't. That means we first need to use a differential cut to prove this equation on the velocity before we then proceed to prove that equation on the position. And, well, actually looking back, that makes some sense, right? Because x prime equals v means how x changes depends on how v changes, but how v changes is written down here, so unless we first understand, for example, this way around, how the value of the velocity changes, we have no way of ever knowing how the value of the position changes. So let's go right ahead with a proof like that. Here's the question. And the first thing we do is introduce a ghost. Fortunately, we've got that proof rule now to remember the initial value of the velocity. Here we go. V naught remember the value that the velocity used to have, such that if we ever need the initial value of the velocity in the rest of the proof, which we'll do in a minute now, we will still have a name for it. It's called V0. Spectacular. Now we do a differential cut to prove that V equals V0 minus Tg is true, by proving that V equals V0 minus Tg is true. And then proceed to prove here to justify that this differential cut was okay. Let's first do the proof. How do we prove that this is the case? Well, differential invariance, right? We put the prime of the formula, which will give us V prime equals minus T prime G, and then we plug in the value of, V prime and the value for T prime. That will require us to prove that minus G equals minus 1 times G, which is really easy to prove by arithmetic. So that worked. And we come back with the proof down here and continue this. Now we introduce a discrete ghost for the position. So we introduce a new variable that remembers the value that the position used to have, no matter what it might be. X0 is whatever initial value x has. And then likewise, we can prove first that a position equation is true, and then assume that the position equation is true after the differential cut. Let's first continue the proof down here. Again, we will use differential invariance to prime the entire postcondition, which will give us x prime equals v0 t prime minus 2g over 2t t prime. Let's look at this. It's the differential of t squared times t over 2. We plug in x prime and we plug in t prime in these places. That requires us to prove that velocity, which is the new value for x prime, equals, well, t prime is 1, but v0 survives, and minus 2g over 2t, t prime is 1, so that goes away. And how can we then prove this? Well, of course, in general we couldn't, but we just put in the evolution domain constraint a knowledge about the velocity's value, which ended up here. And if we assume that v equals v0 minus tg in the evolution domain constraint, then of course v equals v0 minus 2g over 2t, because that just cancels. So that proves by arithmetic. And up here, we now have the entire knowledge about the differential equation, because we've got exactly how the velocity changes as a function of time and how the position changes as a function of time. So what do we do now? Well, we still shouldn't be using the solution axiom, because then we would make all the same trouble yet again, and we would still be using the solution axiom. But what else can we do? Could be using the differential invariant axiom, but then first of all, we probably wouldn't have needed all of this, and second of all, that only works if the postcondition is a very beautiful invariant already. But we can use the differential weakening axiom, because we basically teased out our entire knowledge about the behavior of the variables using the appropriate differential cuts. Now we know so much that even if way back when a differential weakening step wouldn't have been helpful, now it is very helpful. So let's do that. We will get the entire conjunctions of the evolution domain constraints implies the postcondition that we want. Let's spell that out in more detail. Here's the question when we expand what B is. And then we split the proof at a conjunction after we first rewrite the velocity by substituting an equation in, and then rewrite the position by substituting an equation in to get this. Now we can weaken the things we no longer need. We no longer need position, because the position no longer occurs. Well, it still occurs here, but we've got the exact same knowledge on this side, so there's no need to plug in the position. And we can delete the knowledge of velocity and the knowledge of position because it's become irrelevant, and then split the proof at the conjunction to prove the right conjunct is among the assumptions. X squared equals 0 usually implies that x squared equals 0, no matter the fact that x happens to have been this particular value here. And on the other side, here, the proof of this now is independent of that, but it will basically just follow by cancellation. So now things will cancel. If we multiply this out, we get minus v naught square plus 2 v naught tg, left and right hand side, minus t squared g square. And now that cancels because this exactly is that, and this exactly is that. And what we've got remaining is exactly a question on the initial value and the fact that the initial height h was set up correspondingly. So that will follow exactly from the rest of the proof. But the point that I really want to make is here we've used ghost solutions. So we put in an equation telling us exactly the values of variables, change as a function of time. So we did here. Here we use discrete ghosts to remember the initial value of variables. And in fact, of course, our differential cuts will only succeed, and here's an interesting twist, in case these are actually initially true. Are they initially true? I'm glad we left these questions in the proof because they're not initially true. So remember, differential cut, that has to remain some kind of inductive argument, but also it needs to be actually true in the beginning. And well, we don't even know, we do know the value of v naught and v, but we don't know the value that t has in the beginning. So even if in the beginning we do know that the value of v is going to be v naught, we have no way of knowing what the initial value of t is going to be. What could we possibly do to know the initial value of t? Well, we can't know because we don't know anything down here in the proof. But, of course, the actual solution then is going to be v equals v naught minus the change between t minus the initial time, t naught, times gravity. Well, what's the initial time? Well, if we change it like that, then we can also remember, fortunately there's a proof rule for the job, what used to be the initial value of time by a discrete ghost that says, before all of this is happening, let's remember the initial value of t in the variable t naught, and then modify the solution accordingly. That finally gives you a proof, and fortunately, each and every one of those solutions was actually proved to be a solution. But of course, remember, now it's become slightly more awkward. If only we had a way of choosing the initial value of time, because it shouldn't be that relevant in this argument. In fact, what about time at all? I secretly snuck in t prime equals 1 into the bouncing balls proof, but remember, time was never part of bouncing ball quantum's model, not even in its event-triggered version. Only in its time-triggered ping-pong ball version that we introduced time for the sake of writing out time-triggered control. And that seems so unfair. Why does quantum the bouncing ball now have a proof without the solution axiom, but only if we enriched it with time, which shouldn't be part of the original source model? If only, just like the proof rules for inventing initial values of things, what if we also had a proof rule that's inventing time for us? So why does the proof with the ghost solutions need t prime equals 1 in the model? Well, of course it does need them, because otherwise we have no way of knowing what t is. But even if we don't have t prime equals 1 in the model, can't we just maybe simply add it? Well, if we had a proof rule for the job, we could. Here's one. The proof rule that says whatever you would like to prove about a differential equation, how about you add in t prime equals 1? Yeah, well, hold on a minute. Is this an okay proof rule now? Just adding in a differential ghost of time, a new variable that wasn't there, I just needed it for the proof? Is that an okay reasoning principle? What could possibly go wrong? Well, I guess what could go wrong is that we had t prime already. We can hardly add t prime equals 1 into a differential equation x prime equals v with t prime equals 2, because it's going to be very hard for the variable t to simultaneously follow the differential equation t prime equals 2 while also following the differential equation t prime equals 1. At least for any positive duration, that will be impossible. That we can't do We can't already have an ODE for t prime. We also can't use t in the rest of the ODE because we can't add t prime equals 1 into a differential equation that so far just looked x prime equals v and v prime equals t, because this used to make sure that t is not changing and all of a sudden it would be. That would be an entirely different dynamics. That we can't do. But of course we can add t prime equals 1 into a differential equation that one doesn't mention t at all yet. X prime equals v, v prime equals minus g. Speaking of course we can only do that unless the post condition, for example, reads t, because then it's still a broken argument. Because the post condition would express a value of the value that t used to have, and now it's changing by t prime equals 1 up here, and that would be very bad. So the point is, this is a perfectly harmless proof rule, but only for a new variable t. Ghosts have to be new every time we invent them. For once, the problem with this proof rule now is not one of soundness. The problem now is that it's simply overly specific, and this is a perfectly useful proof rule for adding t prime equals 1 into a differential equation, but suppose we ever want to add any other ODE into the dynamics, this proof rule just won't be general enough. So how about we skip worrying about differential ghosts of time and make it more general right away, investigating proof rules that add much more arbitrary differential equations into the dynamics with the differential ghost proof rule. In fact, this time we can render it directly as an axiom and say that if we are interested in the question whether property p is always true after a differential equation, x prime equals f of x, within an evolution domain constraint Q, then we can equivalently prove the same question whether p is true after a slightly bigger differential equation system, the one that, in addition to x prime equals f of x, says, oh, and y prime equals g of xy. So a new differential equation which we dreamt up. Could be one, as in the time example, but could also be a more general differential equation. And, well, we don't know the initial value for y, but we also don't have to, because this axiom now says that property p is always true after an ODE, if and only if it is true after an augmented ODE that has a new differential equation system, y prime equals g of xy, with some initial value for y. And before we do anything else with it, let's directly understand how we can get out of this differential ghost axiom the specific proof rule for differential ghosts of time, just as a special case. Well, we will derive this from the differential ghost principle, like so. So we point to this differential equation and say, please replace the left-hand side of the differential ghost axiom with the right-hand side, where we're at liberty of choosing a new right-hand side for the differential equation, g of xy. And this time it's just a new variable t. Of course, y has to be new here as well. T is new, and we say for t prime equals 1 as the right-hand side, we need to prove this for some initial value of the variable t. Now, the initial value of the variable t we can choose in a clever way, for example, as initial time equals 0. And that means that if we work with the differential ghost axiom, we actually get a proof rule that's slightly more useful than the old differential ghosts of time proof rule suggestion, because it also makes it clear how it was okay to assume without loss of generality that the clock t prime equals to 1 we've just added might as well start at the initial value 0, because the rest of the system didn't depend on it. And that, of course, makes this business of t minus t naught and the solution go away, and it's much more useful for that. More importantly, however, we've got one axiom that can add any ODE. Let's play around with it a little bit. Here's a question about a dynamics that says if we start where x is positive, then x will always stay positive, or if we follow the differential equation x prime equals minus x. That should be true, right? So let's prove it by differential invariance. So that will form the differential of the post condition. That's x prime positive plug in the left-hand side of the ODE for the right-hand side of the ODE, minus x is positive, and how do we prove that again? Well, we don't, right? Because we can't prove that minus x is positive because, well, it might very well not be, right? The numbers 7 as well as minus 7 both exist, and if you plug in 7 for x, minus x isn't very positive at all. So this is not valid. Is the question at the bottom valid? Is this a valid formula? Yes, it is. But the point is that if we follow the behavior of the system over time, then its value keeps on decreasing and decreasing and decreasing and decreasing. That means the question whether x is positive keeps on getting worse and worse and worse and worse and worse because the trend of the entire evolution is always downwards. And it's, in a certain sense, a bit of a miracle that the evolution didn't look like so, right? Which maybe would have been equally possible. Telling this evolution, which is the right solution of this differential equation, that does satisfy that x is always positive. Apart from that one, sort of, that's the question about how the rate of change is changing over time. Let's prove it in a different way. Differential invariants apparently aren't exactly helping, and, well, now you could possibly try differential cuts, but after some effort, you'll see that it also doesn't work, and in fact you can prove this question can't be proved using just differential invariants and differential cuts. Here matters get worse over time, and if we prove it in a different way, matters get better over time. Let's do a differential ghost, introduce a new differential equation, y prime equals y over 2, not just a time variable, a much more interesting differential equation, for some initial value of y. Speaking of initial value of y, we can choose a y that makes xy squared equals 1 true in the beginning. Why could we do that? Well, because if we know that x is positive, we also know that we could have chosen a y such that xy squared is 1. Well, x is positive. If we multiply with a non-negative number and we get 1 out of it, right, that's precisely possible because x itself is positive. It wouldn't have been possible if x would have been either 0 or a negative number, because y squared is always greater or equal to 0. But okay, such a y we can choose, and what could we be doing now? Well, now we could prove by monotonicity that xy squared always stays equal to 1. And that does imply that x is positive, because if we have a proof, just like it's over here, that xy squared is 1, then x must be positive. Why? Well, precisely because y squared is greater or equal to 0. And if a product multiplies to 1 and one of them is greater or equal to 0, the other factor, first of all, can't have been 0, and also had better be a positive number, otherwise this couldn't possibly have been true. So yes, this does imply that x is positive, which was the original question. What do we do over here on this side? Well, fortunately we dreamed up a new ODE, and now we can use differential invariance principles just to form the differential of that. It's a product, so that will give us the left-hand side primed times the right-hand side, plus the left-hand side times the right-hand side primed. So that will give us x prime y squared plus x times 2y prime. And then we plug in x prime here and y prime there, which will give us minus x times y squared plus 2xy times y prime, which is y over 2. Well, and that now proves very easily, because minus xy squared plus the 2's cancel, xy squared is of course 0. So that's very easy to prove. Brilliant. We have a proof. And what the proof did is it introduced a new differential equation, y prime equals y over 2, which was made up arbitrarily, just for the sake of this argument, because it did make the question we cared about, xy squared equals 1, to be a very easily provable invariant of the dynamics. Well, that in its own right doesn't help us a whole lot. This is a relation of original systems variable to ghost variables, but fortunately the ghost variable was chosen such that this particular knowledge about the relation of old and new variables helps us understand also something about the original dynamics, namely, if xy squared is 1 all the time, x must have been positive all the time. In other words, this is basically a dynamics which keeps on holding that one up. Right? It's a counterweight ghost. It's something that says, by way of this relation, that even if the value of x keeps on dropping and dropping and dropping, it's still being held up just enough by this lever here, if you will. Creative proofs with differential ghosts prove what we otherwise couldn't. If we tried this with a differential invariance proof, apparently it didn't work, and if you try anything else with differential invariance and differential cuts, it really won't work. What does that tell us? That tells us that differential ghosts are really powerful, right? They can prove things we otherwise couldn't. That should make us nervous. Can they maybe prove too much? Are differential ghosts actually really sound? They're apparently useful. Are they too useful? Well, this example is fine, because indeed, the solution will always stay positive. Are there other cases where differential ghosts would prove things that aren't actually true? Now, after this gradual introduction into ghost variables, let's understand the differential ghost reasoning principle in full. Here was the axiom, the differential ghosts axiom, that says x prime equals f of x within Q, and always when we follow this differential equation system here, is P true if and only if P is always true after an augmented differential equation system that has y prime equals g of xy in it, still within the same evolution domain constraint, for some initial value of y. What could possibly go wrong? Well, of course, the differential ghost y prime had better be new. It wouldn't be sound if y would already appear either here on the right-hand side of the differential equation that was there before, or within the evolution domain constraint Q, because then we would be limiting it, or within the post-condition P. And that's, of course, all ruled out, because y had better be new. Well, what else could possibly go wrong? The idea is we've got old behavior, new made-up behavior, balancing at a beautiful invariant, which is like dark matter proofs, right? You observe something about the universe, as in physics, and say something isn't the way I expect it to be. My invariants don't balance out. Energy doesn't add up. Maybe there is something that I just can't observe, the dark matter of the universe. If I hypothesize how this dark matter that I can't observe changes, all of a sudden I have a more generalized energy invariant that is actually invariant. The relationship of the old and the new state together makes this generalized energy invariant true. And if I make up this dark matter for proofs in a creative way, I even learn something about the observable part of the universe. What's, however, very important is that, of course, we can hypothesize on a new differential equation for a ghost arbitrarily as we want, but we better make sure it has a solution, because otherwise we would have said all behavior of a system that has a solution are equivalent to the property being true after all differential equations that don't have a solution, which it vacuously is, because if it doesn't have a solution, it doesn't have a solution. That can't quite happen, actually, because in the evolution domain constraint, Q, Y can't appear, and all the differential equations we can write down, addition, multiplication, subtraction, and so on, they all do have solutions. Only short-lived one. And that's what the problem lies. We need to make sure that the new differential equation we're adding in has a global solution for all times, or at least has a solution that exists for as long as x does. Because if x ceases to exist after 17 seconds, then it's okay if y doesn't exist any longer either, because its evolution is the function of x and y, but at least y shouldn't stop existing before x does. And that it exists for sufficiently long is guaranteed if only we make sure that the right-hand side of a differential equation the differential ghost we're making up is linear in the new variable y. So a of x and b of x can be arbitrary continuous functions. You can write them down arbitrarily, higher degrees and higher polynomials, but the new variable should only occur linearly, because if it does, it's clear by the Pika-Lindelöf existence uniqueness theorems that it does have a solution that exists for long enough. Recall chapter 2 appendix, for example. In fact, it turns out also that linear differential equations are enough. This is the differential ghost axiom. We can package it up to a differential ghost proof rule, which, however, essentially does the same thing. It just says replace the left-hand side of this axiom by the right-hand side. So introduce, for some initial value y, the new differential equation, which is linear in the new variable. And we can also package it up in the way we've already used it in the exponential decay example to go one step further and prove that if we ask an invariant question about a differential equation, we can ask another invariant g about an enriched differential equation with a new differential ghost y prime equals a of x y plus b of x, whenever we make sure that the old invariant f is equivalent to, for some y, the new invariant does hold. Why? Well, because in the beginning we do know f, right, in the initial state, and because f is equivalent to g for some y, that also means we know g for some initial value of y that we don't know anything about except that it exists, which is enough. Then we follow this differential equation, which doesn't allow the differential ghost y very much to change along this differential equation. Change is good. But then at the end, by this second premise, g is still true for some value of y that we don't know a whole lot about, but since g is true for some y, we also know that f is true because, hey, they're equivalent, and that means f is true. The derivation of the differential auxiliary principle out of the differential ghost axiom is just precisely a slight abstraction and generalization of what we did for the exponential decay question. Here we go. F is invariant, but the differential ghost axiom, that means there is a y such that add in y prime equals a of x, y plus b of x is true. Then by the monotonicity principle, we can write g instead of f. Why? Well, if g, the new postcondition, implies f, the old postcondition, that's certainly fine if only there were not an existential quantifier by the monotonicity rule, but the monotonicity reasoning principle also applies for the exists quantifier. This is a simple exercise. And here, since y is actually new, it can't have occurred in here. That means proving that f follows from the existence of a y such that g is enough to establish that g implies f, because, well, even if y occurs here, it can't possibly have occurred on the right-hand side by the freshness condition. On the other side, you do use the exists right proof rule to choose a witness for which indeed g holds true afterwards, which means you can prove with a cut that g holds true, and then prove that g is an invariant. And these two questions together are exactly that question here. What could possibly go wrong? Well, we said it is important for the differential ghost proof rule and the differential ghost axiom that it stems from that the solution is actually linear in the differential ghost variable. Why is that important? Well, because otherwise we could prove that if we start at x equals 0, x prime equals 1 satisfies x less or equals 6 all the time by introducing a new differential ghost such as y prime is y squared plus 1, and then prove a witness such as initially y is 0 with y prime equals y squared plus 1, and then this is actually a valid formula even if that is not, and that's really bad because y prime equals y squared plus 1, starting from y equals 0, has as solution the tangent function. And why is that complicated? Well, because the tangent function explodes in finite time, whereas the original x prime equals 1 does not. And indeed, this is only possible because this is a nonlinear function in the new variable y. Explosive ghosts stop the world. Don't ever explode the world, and don't use explosions in your proofs because, for example, it doesn't help you make an argument that your car doesn't crash by composing it with an explosive device or a differential ghost that stops the world in finite time, because an argument that says, well, no collision happened during the remaining half a split second that the nuclear bomb worked on, doesn't mean that the system will still be collision-free back there, right? You need to actually have an argument for the true behavior of the system, so any augmented differential equations that you put in need to still have solutions while your original source system has solutions. Having seen how useful differential ghosts are to prove properties, the curse is that you need to dream up their differential equations. Well, that's also their blessing, because you can dream up their differential equations. So whenever you're infinitely creative, you can do infinitely useful proofs. But how do you come up with the differential equations from the get-go? Remember back the exponential decay example. By the differential ghost principle, we can dream up y prime equals, I don't know what it was, but the point is that we already essentially know, just from the arithmetic, that a good question to ask instead of proving x greater than 0 is to prove that xy squared equals 1 for some y, because, hey, these two formulas are equivalent. So if we prove this to be an invariant, we have successfully proved that x positive is an invariant as well. What do I put in for the differential ghost y prime? Well, how about I punt on that nebulous question for a moment? What I do know is that the next step I would like to do here is to use the differential invariance proof rule. Well, that will give me, after you refer to over here proofs, that x prime y squared plus x to y prime equals 0 for a discrete shadow of the differential equation system we already know, plus a discrete shadow of the admittedly nebulous differential equation. But we can certainly plug in the new value for x prime and plug in the, well, admittedly spooky new value for y prime. That will give us minus x y squared plus 2xy, ugh, spooky cloud. Okay. That was spooky. I guess, however, after this sketchy proof, we could now look at the spooky cloud and figure out what is it that I would have to plug in for the spooky cloud here to make this proof. So I have to plug it in here to make sure that's what I get here, which means I have to plug it in here to make sure that's what I get there, and the whole thing proves. Now, however, it's very easy to investigate what to plug in for the substitute ghost, namely something that solves this minus xy squared plus 2xy equals 0. And for the I have to plug in precisely y over 2, because if I have a y here, I have another y squared, and if I have an over 2 here, then the divided by 2 cancels with the 2, which exactly makes the entire thing cancel. So I could prove this if only the spooky cloud were y over 2. Well, how about I ask the substitute ghost to drag and drop itself in, instead of all of these cases, write down y over 2. If you're careful, like me, maybe you would like to go back and redo the proof from the beginning now that you've constructed the right answer. Or you can work slightly more systematically with this recipe for brewing suitable differential ghosts, but just doing the proof and then fill in the blanks that you were unsure about, construct it to make the proof work out, by instead working with a function symbol j of y that plays the role of the substitute ghost and is slightly more civilized. So certainly we could work with y prime equals j of y, because the right hand side is going to be a function of y, that's for sure, and then plug this in here and here and here everywhere, and then take the entire proof and say I could prove this if only I were to replace the function symbol j of y with y over 2, which you can actually substitute in uniformly, as we will see in the 18th chapter of this textbook. Of course, even when doing that, we still have to make sure that the differential equation we're plugging in for the differential ghost actually is a linear differential equation in the new variable y. It can be arbitrarily complicated in the old variables, but not in the new ones, to make sure the solutions exist for long enough. Using what you've just seen, you can, in fact, solve any arbitrary differential equations without using the solutions axiom. You've essentially seen that, but let me talk you through this more carefully one more time. If we have any arbitrary question about a differential equation, we can use the differential ghost to dream up a time variable even if it wasn't there. That's just a differential ghost use. We can make sure the new time variable starts as a convenient value 0 just by using that as a witness. And then with a differential cut, we plug in the solution of the velocity. Having done so, when we prove it on the side, we plug in the solution of the position. Of course, we prove it on the side. Having done so, we can take the original post condition and transform it over by the differential weakening axiom into assuming the evolution domain constraint, which now has become informative, and then transform the post condition using the evolution domain constraint, which now talks in terms of the new differential ghost variable t, but no longer mentions x or v, but merely mentions the discrete ghosts that are elided here just for the sake of clarity of the proof. And then we can again use a differential cut in the backwards direction to delete this solution and part of the evolution domain constraint. Do that again with the velocity. Now we can use an inverse differential ghost, because remember it was an equivalent, so just like we could use it back there to introduce a time variable, now we can use it in the backwards direction to delete a position variable. Why? Well, only because we didn't mention it anymore in the argument, and having done so, we can also use the differential ghost axiom in the inverse direction to delete the velocity. Why? Well, because we don't mention it. And now we're down to a very simple differential equation, one that's essentially just time, just one variable with a constant right-hand side. That we can solve easily using the DS axiom that we'll see in the 18th chapter as well, for example. To solve this one as well, that's essentially just time, and plug it in and have precisely the solution of the differential equation without ever having called the original solution axiom that we worried about. These are solvable ghosts. On the side, of course, you have to prove that the velocity solution was actually a solution. We have to prove, having done so, that the position solution is actually a solution. And now you have overall proof. If only v equals v naught and x equals x naught are actually true in the beginning before the differential invariant proof rule is used, which they won't be except discrete ghosts to the rescue. You can make sure the two are equal just by having x naught remember the initial value of x and having v naught remember the initial value of v. Discrete ghosts can remember initial values on demand. Okay, let's put differential ghosts to more use, more than exponential decay and exponential climbing and so on, but they're semi-exciting only. For example, we can look at an aerodynamic bouncing ball property. Never mind the bouncing for now, because that's discrete dynamics that we already understand beautifully ever since the first part of this textbook. But what happens in aerodynamics, what you have is that the bouncing ball is falling according to x prime equals velocity, and the velocity is changing according to gravity. V prime is minus gravity, but also with a aerodynamic resistance that is proportional to the square of the velocity and is working against the velocity. So it's slowing the bouncing ball down as the bouncing ball is falling further to the ground. So if we only worry about the part of the behavior where the position is above ground but the velocity is already falling, then in this particular case, is this the right differential equation? X prime equals velocity, and velocity prime is minus gravity plus some aerodynamic resistance r times velocity squared. And then in that case, well, it should be easy to prove that, for example, you're above ground and that the velocity is less or equal to 0, but can we also prove an upper bound on the velocity? Well, because the velocity will keep on increasing in absolute value according to this differential equation, but not arbitrarily. At some point, we'll reach the limit velocity. And how we can derive that is the limit velocity, I guess, will happen when the velocity no longer changes, which means when v prime is 0. What is v prime? That's that. So it will happen, I guess, when minus g plus rv squared is 0. What is that? Well, we can solve for velocity for the job. That happens when, I guess, velocity is something like plus or minus the square root of g over r. That was admittedly a heuristic derivation, but we can now do a proper proof for it. We can state, for example, that we always have velocity above minus square root of g over r. Remember, it's going downwards, right? The velocity is negative. But it will always be lower bounded by minus the limit velocity of falling in the air, which is square root of g over r. Of course, that is only true if we start above this limit velocity also. But now we can do a proof. This again is a property that apparently is getting worse and worse and worse and worse over time. We keep on approaching this limit velocity, but we never reach it, which means we need a differential ghost for the job. Proving that it is above this limit velocity will enable us to prove that with a differential ghost we make up arbitrarily y squared times the velocity plus the square root of g over r is 0, because if that's the case, then clearly the velocity must be above this value, because otherwise it wouldn't multiply up to 1. So we continue the differential invariance proof for this. Take the differential of the post condition, which is 2y prime times whatever we got here, plus y squared, and the differential of this, that's the constant, so that's just v prime. Well, v prime we do know, y prime we don't know. Let's plug this in. That's 2y prime. Well, that doesn't have a value that we're using substitute ghosts, so we only know that it's going to be some function of x and v and y. The rest stays, but the v prime we do know. The v prime is here that we're plugging in, so it gives us minus g plus rv squared. Now we can cancel this out, and we will find out that the right value to have for the substitute ghost is this. Solve this for yourself to make sure you understand. And that is precisely constructed to make sure that the arithmetic actually proves at the end. The point is that with a differential ghost that we construct with a substitute ghost one step at a time, can we easily prove this limit velocity argument for an aerodynamic bouncing ball. To summarize, what we've seen now are the three fundamental axiomatic reasoning principles for differential equations. The differential invariant principle that says even if the solution of a differential equation is complicated, for proving that we never enter a bad blue region, it is sufficient to prove that, well, our dynamics never pushes us from safe into unsafe. And if we start safe, then due to this differential reasoning, the reason by direction in which we evolve, we can prove that if we only evolve in a direction where p is getting more true, at least not less true, then the property is actually true. Differential cut principle, which is another logical reasoning principle, not induction, but cuts. So first prove a lemma, then use a lemma. We first prove that we can't enter the red region. We can snip it and cut it away out of the state space. Having done so, we might want to do that repeatedly and prove that we can't enter the other red region either, so we can cut it out of the state space. And now look at the state space and say, no wonder the system is safe, because we ran out of bad blue regions, so differential weakening will do the job for us. So in pictures, if we prove that we can't leave C, we might as well assume from now on that we can't leave C. And the new differential ghost principle that says that sometimes when proving a property of a differential equation, it can be helpful to dream up a new differential equation arbitrarily out of thin air. Just make up a new differential equation y prime equals g of xy, linear the new variable to make sure its solutions exist for long enough. And if we do that in a clever way, for example, substitute ghosts tell us how, then we can make sure that the new augmented system of the old and the new variables satisfies an invariant that is easily provable, And if we do it in an even more clever way, also make sure that from the invariant and the augmented system of x and y, we learn something about the behavior of the original system, x prime equals f of x. So in addition to the dynamics, we make up some new dynamics arbitrarily, which is unrelated to the evolution domain constraint. Linear, however, in a way that helps us do the proof. Here are the proof rules summarizing what we've now seen. Differential invariants prove post conditions to be invariants by proving the differentials to be true after assignments of the right hand side of the ODE to the left hand side of the ODE in the evolution domain constraint. Differential cuts edit the evolution domain constraint of a differential equation after first proving that that was okay, after proving that we can't leave C. We might as well assume that we can't leave C. Differential ghosts edit the differential equation in a linear way, remember, and for example, packaged up in the differential auxiliaries principle such that we prove another invariant that is equivalent to the old invariant for a new invariant G that for some value of y is equivalent to the old invariant P holding